Dear students, I am going to describe the third experiment of your engineering physics lab cycle, spectrometer characteristic wavelengths.
This figure shows the spectrometer instrument. Now let us see the aim of this experiment. There are two aims. The first aim is to identify the given source of light by determining the characteristic wavelengths of the prominent lines of light emanating from it using spectrometer based on the theory of diffraction. The second aim is to find the dispersive power of the given plane transmission grating, which is the optical element used to disperse polychromatic light into its components. The apparatus used in this experiment include mercury vapor lamp, plane diffraction grating, reading lens, spectrometer. Before going deep into the experiment, let me ask you one question. How do scientists determine the chemical compositions of distant planets and stars? The most common method astronomers use to determine the composition of stars, planets, and other objects is spectroscopy. Today, this process uses instruments with a grating that spreads out the light from an object by wavelength. This spread out light is called a spectrum. Every element and combination of elements has a unique fingerprint that astronomers can look for in the spectrum of a given object. Identifying those fingerprints allows researchers to determine what it is made of. This figure represents the absorption spectrum of hydrogen atom, where the intensity is plotted as a function of wavelength. This figure represents the sodium absorption spectrum. The fingerprint that I mentioned earlier often appears as the absorption of light. Every atom has electrons, and these electrons like to stay in their lowest energy configuration. But when photons carrying energy hit an electron, they can boost it to the higher energy levels. This is absorption. And each element's electrons absorb light at specific wavelengths related to the difference between energy levels in that atom. But the electrons want to return to their original levels, so they don't hold on to the energy for long. When they emit the energy, they release photons with exactly the same wavelength as that were absorbed in the first place. An electron can release this energy in any direction. So most of the light is emitted in directions away from our line of sight. Therefore, a dark line appears in the spectrum at that particular wavelength. Because the wavelengths at which absorption lines occur are unique for each element, astronomers can measure the position of the lines to determine which elements are present in a target. The amount of light that is absorbed can also provide information about how much of each element is present. Each substance will either transmit or absorb light, and the wavelength by which the substance does this identifies what the substance is. This is the electromagnetic spectrum. This region represents the visible region of the electromagnetic spectrum, spanning from 400 nanometers to 700 nanometers of wavelength. Our aim is to measure such a minute quantity, the wavelength, which is of the order of 10 raised to minus 9 meters. A spectrometer is an optical instrument which is used to analyze light emitted by a given light source to identify the characteristic wavelengths with their respective intensities, which in turn reveals the energy levels within the source of light. Since wavelength of light is of the orders of certain nanometers, it clearly is not something that can be measured as easily or as simply as units of distance or weight. Hence, here we use an indirect method of calculating the wavelength of light simply by allowing the composite light to disperse and thereby measuring the angle of diffraction of the constituent colors. In order to disperse, generally, the composite light coming out the source is allowed to pass through optical elements like prism, grating, etc. Here we use a plane transmission diffraction grating for this purpose. Now let us see the important parts of a spectrometer. A spectrometer has four main parts: the telescope, the collimator, the rotating table, which is also known as grating table, and the rotating base. This is the mercury vapor lamp which is used as the source of light in this experiment. It emits white light which consists of 7 different colors which can be dispersed with the help of a grating or a prism. Now let's see each part of the spectrometer in detail. Collimator's purpose is to produce a parallel beam of light. It consists of a horizontal tube of variable length with an adjustment slit at one end and a convex lens at the other end so as to produce a parallel beam of light. This figure shows the slit which is placed on one side of the collimator. You can adjust the width of the slit with the help of this knob. The second important part is the telescope. The telescope consists of an objective O at one end and an eyepiece fixed with the cross wires on the other end. The telescope is fixed to the circular scale graduated in degrees. The telescope can be turned with the scale about a vertical axis passing through the center of the spectrometer. The eyepiece of the telescope is provided with cross wires. The telescope can be fixed in any position by the main screw. Fine adjustment can be made by a fine adjustment screw which is tangential to the main screw. The third important part of the spectrometer is the rotating table, and it consists of an upper plate and a lower plate separated by 3 springs. These screws pass through these springs. The rotating table P can be mounted in any position by means of a screw at its bottom. The rotating table can be rotated about the main vertical axis as the telescope. These two figures show the diffraction grating which is used to disperse the white light into its component colors. The fourth important part of the spectrometer is the rotating base. The telescope and the prism table or the grating table are mounted on an independently rotating base. The vernier scales provide measurement of the relative position of the base to within 1 minute of arc. The working principle here is the dispersion via diffraction. Here, the dispersion of the polychromatic light is done by a diffraction grating and using the phenomenon of diffraction as different from that due to prism, which is based on the principle of refraction. In diffraction phenomena, Waves emanating from different spatial points of the source interfere to give rise to a diffraction pattern on the screen. A grating element is essentially a dispersion element which deviates different wavelengths of a polychromatic source of light into different spatial positions. The deviations produced by a grating element is given by the equation sin theta is equal to nn lambda, which is known as the grating equation, and that means that the most deviated wave is the larger wavelength as different from prism dispersion, where most deviated wave is the one with larger frequency or lower wavelength. From the dispersed polychromatic light, the individual wavelengths composing it could be identified along with the information about their relative position, relative number of photons contained in it, or their intensities. As it is not possible to measure wavelength, which is usually of certain nanometers directly, here we use an indirect method of determining it by measuring the angle of diffraction of each component colors with the help of a spectrometer. Then the wavelength corresponding to each diffraction angle can be calculated by using the grating equation sin theta is equal to nn lambda, where small n is the order of the spectrum, capital N is the number of slits per unit length, lambda is the wavelength of light, theta is the angle of diffraction. Hence, the wavelength of each prominent line is given by lambda is equal to sin theta by small n into capital N. Now, the dispersive power of that grating can be calculated using this expression d theta by d lambda is equal to cos theta by nn. This figure explains the difference between prism spectra and diffraction grating spectra. In the case of a prism, spectrum is formed by means of a refraction and dispersion, while a grating spectrum is formed by means of diffraction and dispersion. Red is the most deviated wavelength in grating spectrum, while violet is the most deviated wavelength in the prism spectrum. Here in grating spectrum, violet is the least deviated one, whereas in prism spectrum, red is the least deviated one. Many orders of grating spectrum can be formed with the help of a diffraction grating, whereas the prism spectrum, with a prism we can produce only a single spectrum. Now let me explain the procedure in detail. The preliminary adjustments of the spectrometer include the following steps. Turn the telescope to a white wall and adjust the eyepiece to make the crosswire clear without parallax. Turn the telescope to a distant object and adjust the racking pinion of the telescope until the distant object is clearly seen without parallax. Now illuminate the slit and bring the telescope in line with the collimator. Adjust the rack and pinion of the collimator to make the slit clear. Now make the slit as narrow as possible by adjusting the screw. The next step is to achieve normal incidence. Normal incidence represents the condition in which a wavefront is parallel to the interface, that means the grating, such that the ray path is perpendicular or normal to its surface. So in this case, the angle of incidence is 0, because angle of incidence is the angle at which this light ray is incident with respect to the normal to the surface of this grating, that is this along this direction. So the angle of incidence is equal to 0. The angle measurements become accurate when this particular condition is achieved. To achieve this condition, make the following arrangements. Bring the telescope in line with the collimator to get a direct image of the slit at the crosswire and clamp the telescope. Now clamp the telescope. Now rotate the vernier table until the reading of the vernier 1 is 0 and clamp it. So this represents the 0, 0 setup of the vernier. There are two verniers and this represents one vernier. And it has two scales. One scale is the main scale. This represents the main scale. And the other one is the vernier scale. The main scale can be used to measure angle or readings from 0 to 360 degree. The vernier scale is used to attain accuracy and it consists of 30 divisions. The reading on one vernier is 0 degree implies that the 0 of main scale coincides with the 0 of vernier scale. Now the reading of the other vernier will be 180 degree. That means 180 of the main scale coincides with the 0 of the vernier scale. Now, if you mount the grating manually, the normal incidence condition may not be achieved as the angle of incidence can have any value like 1 degree or 30 minutes or sometimes 0 degree. To ensure that the normal incidence condition is achieved, we should first get a reflected image of the slit. When you get a reflected image of the slit, the angle of incidence will be exactly 45 degree. To achieve that, unclamp the telescope and rotate it through 90 degree and then clamp it. So now 0, 0 of the vernier is set. Now we are going to unclamp that telescope and rotate it through 90 degree and then clamp it. Now mount the grating on the grating table with its rulings vertical as shown here. And then clamp the grating table, that means this rotating table, with the help of this screw. Now in the next step, rotate the grating table along until the reflected image of the slit is exactly at the crosswire of the telescope. So this is the telescope. And then clamp that grating table. Now the angle of incidence with respect to the normal of the grating surface is exactly 45 degree. This angle represents the angle between the incident ray and the normal to the grating and is 45 degree. Similarly, the angle between the telescope and the normal to the grating surface is also 45 degree. So now the angle of incidence at the grating surface is 45 degree exactly. But our aim is to achieve normal incidence, which means that the angle of incidence is 0 degree. How can we achieve that? To make the angle of incidence exactly 0 degree, that is normal incidence, unclamp the vernier table and rotate it through 45 degrees along this direction so as to nullify the already existing angle of incidence of 45 degree and to make the surface of grating normal to the collimator, then clamp the vernier table. Now, in the last step, rotate the telescope through 90 degree so as to make all parts of the spectrometer in a straight line as shown here. Now you can see a spectrum like this. Let us assume that the bottom part of the spectrum shown in this figure represents the left side of the central maximum and the top part represents the right side of the central maximum. This is the central maximum, which is formed due to the undeviated or undiffracted rays emanating directly from the source. These are the first order spectral lines on the right side of the central maximum. So blue is the least deviated one and it appears near to the central maximum. Then comes green, followed by two yellow lines. These are the first order spectral lines on the left side of the central maximum. Central maximum will be somewhere here. Then blue color will be the followed by green, then two yellow lines. To standardize the grating, unclamp the telescope and bring it in a line with the collimator to get the direct image of the slit. From this position, move the telescope slowly towards the left until first order spectrum is observed. By adjusting the tangential screw of the telescope, the vertical cross wires can be made to coincide with the green line of the spectrum. Take the vernier readings. Now move the telescope to the right side and the crosswire is made to coincide with the green line on the right side. The difference between the readings gives 2 theta and then calculate theta. The wavelength of mercury light is 5460 into 10 raised to minus 10 meters. Using this, calculate n from the relation n is equal to sine theta by n lambda. Once the grating is standardized, we can take the readings to find the wavelength of spectral lines. So now, move the telescope slowly towards the left end until first order spectrum is observed. This represents the spectrum on the left side. The central maximum can be seen somewhere here. Then blue, violet, blue, etc. Violet, blue, green, yellow, etc. And there are two yellow lines. This inner one actually represents yellow 2 and the outer one represents yellow 1. By adjusting the tangential screw of the telescope, the vertical crosswire is made to coincide with yellow 1 line. That means this outer line. Take the vernier readings. Now move the telescope to coincide with the successive lines like yellow 2, green, etc. And take the vernier scale readings from both verniers. Then move the telescope to the right side and take the corresponding readings of the verniers. So this represents the spectrum on the right side, and in this spectrum, this one represents yellow 1 and this inner one represents yellow 2. So take the readings from blue, then green, yellow 2, yellow 1. So this represents the observation table. You can see the readings for the left spectrum and for the right spectrum. The difference between these two readings, left and right, actually gives 2 theta, and then find out the mean of this 2 theta corresponding to the 2 vernier readings. That will actually give you mean 2 theta value, and then divide it by 2, that will give you theta. Substitute the value of theta in the grating equation, then you can easily find out lambda, which is equal to sine theta by nn, and here we are dealing with first order spectrum, so small n is equal to 1. And here we actually use 2 verniers just to make sure that the readings are accurate. Now considering 2 closely spaced lines like yellow 1 and yellow 2 on both sides of the central maximum, it is possible to calculate the dispersive power of grating. So the dispersive power of a grating is defined as the ratio of the difference in the angle of diffraction of any 2 neighboring spectral lines to the difference in wavelength between the 2 spectral lines. It can also be defined as the difference in the angle of diffraction per unit change in wavelength. The diffraction of the nth order principal maximum for a wavelength lambda is given by the grating equation a plus b sine theta is equal to n lambda. Now just differentiate that expression, then we will get a plus b cos theta d theta is equal to n d lambda, and from that we can rewrite this expression as d theta by d lambda is equal to n prime by cos theta, where d theta by d lambda represents the dispersive power, small n is the order of the spectrum, n prime represents the number of lines per centimeter in the grating, and theta is the angle of diffraction for the nth order principal maximum of wavelength lambda. This is the tabular column for finding out the dispersive power of the grating. Here we need to consider the readings of 2 closely spaced lines, that is yellow 1 and yellow 2 on both sides of the central maximum. Find out the value of theta 1 for yellow 1 and the value of angle of diffraction theta 2 for yellow 2. Then calculate the difference between theta 1 and theta 2. Similarly, find out the difference between the lambda values which we have already calculated, and that will give you d lambda. Then dispersive power is d theta by d lambda. Before taking the readings, you need to determine the least count of spectrometer. Since we have a main scale and a vernier scale on both verniers, the total reading will be MSR plus VSR into least count. To calculate the least count, consider the divisions from 0 to 10 in this figure. How many small divisions are there in between 0 and 10? On the main scale, 20 divisions are there. So 20 divisions on the main scale actually represents 10 degree. 1 degree is equal to 60 minutes. So that means 20 divisions on the main scale is equal to 600 minutes. So 1 division is equal to 10 degree divided by 20, or 600 minutes divided by 20, and that is 0.5 degree, which is also 30 minutes. Now the total number of divisions on the vernier is 30. Least count is defined as the ratio of value of one main scale division to the total number of divisions on the vernier. So that is 30 minutes divided by 30. So that is equal to 1 minute. So the least count of this spectrometer instrument is 1 minute. Now let us see how to take readings, vernier readings. Here is a sample reading for you. In this case, the zero of the vernier lies between 358 degree 30 minutes and 359 degree. So we take the MSR value as 358.5 degree or 358 degree 30 minutes. The minimum value is to be taken, so 358 8 degree 30 minutes. Now check among these 30 divisions on the vernier scale which one exactly coincides with any one of the main scale divisions. Here the 16th division coincides exactly with the main scale division. So we take the VSR value as 16, multiply that by the least count. So that will be 16 minutes plus MSR value which is 358 degree 30 minutes. So 30 minutes plus 16 minutes is 46 minutes and we have 358 degree. So 358 degree 46 minutes is the reading. This shows another sample reading. Here the MSR value 0 of this vernier scale actually lies in between 169 degree 30 minutes and 170 degree. So we have to take the minimum value, that is 169 degree 30 minutes. Then find out which line exactly coincides with any line of the main scale. That actually gives you the vernier scale reading. And then MSR plus VSR into LC will give you the total reading. So that's all about this experiment. Happy learning. Thanks for watching.